In this video, we're going to discuss the full wave bridge rectifier circuit. So on the left side, we are going to apply an AC signal, that is an alternating current signal, to a transformer. Now to the right of this transformer, we have 4 diodes connected like this. And the way these 4 diodes are connected will allow us to convert an AC signal into a DC signal, which is the main purpose of a rectifier. So this is going to be the output of the bridge wave rectifier. Now let's put a resistor here. Let's call it resistor R. Now we have 4 points of interest. So let's call this point A, point B, point C, and point D. And this is going to be D1 or diode 1, diode 2, diode 3, and then diode 4 on the upper left side. And so this is the basic picture of the full wave bridge rectifier circuit. This is how it looks like. Now let's talk about the operation of this circuit. And so here is an AC sine wave, and during the positive half cycle of this wave, the top part of the right side of the transformer is going to have a positive potential, and the left side will have a negative potential. So that's going to be the polarity of the secondary side of the transformer. Conventional current will always flow from a high potential to a low potential. Now keep in mind, this is in the opposite direction of electron flow. So electrons actually flow in the opposite direction. So the green arrows will represent the flow of conventional current. So it's going to flow from the positive terminal of the transformer towards point A, and then from point A towards point B through D1. Now, is D1, is it on or off? Is D1 in forward bias mode or reverse bias mode? So anytime the direction of conventional current, if it's in the same direction of the arrow, the diode is on. It's active. It's on forward bias mode. Now let's say if the current is in the opposite direction to the arrow that's part of the diode symbol. In this case, the diode is in the off mode. It's not active. It's in reverse bias mode. So here we have the arrow, the direction of the current in the same direction as the diode arrow. So therefore D1 is on. It's active. It's in the forward bias mode. Now, will current flow from B to C? Is that going to happen? Notice that the arrow of the diode and the direction of the current, they're opposite to each other. So therefore, that's not going to happen. So let's put an X here. So we could say that D2 is off. So the electric current has no choice but to flow from point B through the resistor and then back towards point D. Now what's going to happen when it reaches point D? Will it go through D4? Because the current will be in the same direction as the diode arrow. Now, there's no point for it to return back to point A because it was already at point A. And whenever you see that, it's not going to work. And so D4 is in reverse bias mode. D4 is off. Another way you can think about it is to understand that the electric potential at point D is less than the electric potential at point A. Current will not flow from a low potential to a high potential. It doesn't work that way. Electric current will always flow from a high potential to a low potential. That is conventional current. So let's say that point A was at 20 volts. Point B will be at 19.3 volts. A typical diode has a voltage drop of 0.6 or 0.7 volts. Now there's going to be a voltage drop across this resistor. And let's say it's probably going to be 0.7. The voltage drop is really the difference between 19.3 and 0.7. So the electric potential at the other side of the resistor is 0.7. And going through D3, point C will be at 0, because that will be the opposite side of this transformer. So D is still 0.7. Current will prefer to flow from a high potential to a low potential, that is, from A to D. However, the arrow of the diode is opposite to the direction of that current, so it's going to be off. And current will not flow from a low potential to a high potential. It's not going to go from 0.7 to 20. And so that's not going to work. Therefore, either way you look at it, diode 4 is off. It's in the reverse bias state. It's not active. So once the current reaches point D, it's not going to go through D4. So that's not going to happen. Therefore, it has to go through D3. So D3 is going to be in the active state. Then from D3, it's going to reach to point C, and then it's going to go back to this transformer. And so that is the direction of the flow of conventional current during the positive half cycle. Now, let's focus on the resistor. We said that current flows from a high potential to a low potential. So the top part of the resistor is at a higher potential than the bottom part of the resistor. Now, in order for us to get DC current or direct current, the polarity of this resistor must remain the same for both the positive half cycle of the AC sine wave and the negative half cycle of the AC sine wave. So we see that it's positive at the top for the positive half cycle. Let's see if it's going to remain the same for the negative half cycle. So let me just get rid of some of the things that I wrote on this picture. Let's see how far this software will allow me to go back. So now, this is going to be the negative half cycle. So the polarity at the right side of the transformer will be reversed. The top part will have a negative sign this time. As always, conventional current will flow from the high potential towards the side with a lower potential. So it's going to emanate from the positive terminal and flow towards the negative terminal. So it's going to flow towards point C. And then from point C, the current will flow towards point B. That is through D2. And so D2 will be in the active state. It's not going to flow through D3 because, as you could see, the diode arrow and the direction of the current, they're opposite to each other. So D3 is inactive. It's off. So as current flows from C to B, it's going to pass through the resistor, going in this direction. So notice that the top part of the resistor is still positive, and the bottom part is still negative, because current will flow from a high potential to a low potential. And so therefore, the polarity across that resistor is the same. Thus, we now have a DC signal as opposed to an AC signal. And so the full wave bridge rectifier circuit is very useful if you want to convert an AC power source into a DC power source. Now let's continue with the flow of the conventional current. So it's going to flow towards point D. Now, will the electric current flow through D3? To answer that, let's put some numbers on the board. So we're going to say this is at a potential of 0 and this is at a potential of 20. So going from, let's say, C to B, there's going to be a voltage drop of 0.7, which means that the potential at B will be 19.3. And then going through the resistor, the potential is going to be at 0.7. And then going to point D, it's still at 0.7 because all we have is just a wire here. And so at point A, it's at 0. Point B is at 19.3, and at point C, it's at 20. So this will help us to tell which diodes will be on and which ones will be off. So now that the current is at point D, it's not going to go through D3 because if it goes in this direction, notice that it's going from a low potential to a high potential, and that's not going to happen. So once again, D3 is still off. Now it wants to go through D4 because the current is going from a high electric potential to a low electric potential. And so D4 will be on, it's active. Now once it reaches point A, it's not going to go to point B because you're going from a low potential to a high potential. And so that's not going to work. So D1 is off as well. So only D2 and D4 are active during the negative half cycle. Now once the current reaches point A, it's going to return back to the transformer. And so that's going to be the flow of conventional current in this circuit during the negative half cycle. Now what type of wave will we get at the output of this circuit? How will it look like? So at the output, we're going to get a pulsating DC signal that looks like this. And if we extend the AC signal at the input, it will look like this. So basically, the negative part of the AC sine wave gets flipped over the x-axis. And so this is going to be the output signal that we'll get for this particular circuit. So we have a pulsating DC signal, as you can see here. Now, when designing a power supply circuit, what you want to do is you want to get a nice, consistent DC signal. Ideally, you want a signal to be like this. You want it to be as smooth as possible. You don't want a pulsating DC wave. So how can we convert this pulsating DC signal into a more smooth DC signal? How can we do that? What elements can we add to this circuit to basically reduce the variations in voltage that we see at the output? Now, one of the first things that we can do is that we can add a capacitor parallel to the resistor. And the capacitor will basically filter out variations in voltages. So without the capacitor, we would have basically a pulsating DC signal that looks like this. But with the capacitor, the variations will be less. It will be more smooth, so to speak. So this is the positive terminal of the capacitor, and this is going to be the negative terminal of the capacitor.